So I have not really a talk, it's more a presentation of the software SpectroCalc 2. I present the first version of the software at the first meeting 2019. Simple words, why I have developed the software was that reason that at the beginning of my spectroscopy career I needed around 6 different software packages to come from a 2D data, from raw data from the camera to the finished spectrum. And it took very long time to make this data reduction for each object. And if I had breaks, and it's sadly often that I have months of breaks with my spectroscopy, and I did it again. It was very hard to come into all these different software types and using of this. And so I decided to develop a software which builds my complete workflow from the data reduction to the end of the spectrum in one software. I presented it here, and there were different discussion about and suggestions, and so I went at home after this event and I decided to write a complete new one software. The reason was that I wanted to be more flexible, that also other people can use this software for their setups. And I think with SpectroCalc 2 I'm now at a point that it's for non-echelle spectra possible to do the most of your applications. So as I said, it is not a talk, so I will go to the software itself and go through the example. The example is VV-SAFE. We have seen it from Ernst yesterday. And the example data are not my best, because I want to show some features of the software where you can better see on not so good data as on good data. If you start the software left above, you have 2 sections. The left middle section is the start with raw data from your camera. And if you have already reduced data, you can go to the right side to make your wavelength calibration or to make post-production of your spectra. So we want to start with raw data. Here you can import your spectra. I have here example with 10 VV-SAFE spectra, each with 8 minutes exposure time. I import this. And a new window appears here with a list of this single spectra, and also automatically you get a graphic with an automatic scan of this data. You have here each single spectra in this graphic, and you have here the ADUs of the camera, and in the x-axis are the pixel numbers. What you can see is, for example, these red dots here are hot pixel. So we need a dark frame correction. So we can import also the dark frames. In my case, I have a dark frame library, so I have a master dark already. But you can also import your single dark frames, which you have done on the same evening or same night. And the master dark is built automatically. I use here my master dark from the library. And normally you have here the list of your single darks, but I have only one, so it's the same as the master dark. If I save it, it will be calculated automatically, and you see that the hot pixels disappeared. So you have the possibility to uncheck this and have the same in real time, the same situation without dark frame, and if you check it, you have it with dark frame. The dark frame correction is very important. If you have a camera, yes, for the hot pixel it's sure, but also for the dark current itself. If you have a camera with a high dark current, this is a subtractive correction. That means if you have, how in this case, a continuum and a peak of a line, an absorption line, or in this case an emission line, this ratio of continuum to the peak is changing after this correction. That means it goes higher. I cannot show it in this example because my dark current is very low, so you will see only the third comma change. But we will see it later on the sky background correction. It is similar to this. So what we also have in this case is from a reference lamp spectrum, and I suggest always to do, if you have more than one spectrum, to do a reference spectrum to start with it, and in between of each spectrum another reference spectrum. Why? Because of the temperature shift you can have during the night. So in this case I have 11 single reference spectra from argon neon. This is the internal argon neon source in the Polaris spectrograph. So you get new windows, one with all these single reference spectra, and one with the list of it. So the next what we have is flat field. Flat field in principle makes a correction of a part of your instrument's response, so the optical part. But it's also not only changing your curve of continuum, also if you have dark spots, dust on your chip or such things, it's important to have a flat field and correct it to avoid artifacts. So flat field is a division, so it's not so critical like a dark frame. In this case I have made 16 flat fields. And you can also have dark frames for the flat fields. In my case, about this low dark current, I use only bias as dark frame. So, and now all the single flat fields are dark corrected, and we can save it as master flat. Sorry. So what we can see in the graphic is that the flat correction, we can also disable it, will change a little bit in the shape of the continuum. Okay, I forgot we can have also dark frames for the reference lamp. So it's also in this case a very short exposure time, and I use the bias as dark frame. So now we have the 2D calibration finished. Why we can see the spectra from the beginning? The system search for the spectrotypes automatically, but I never trust this, a computer program, also not my own. So you have the possibility to control this. With the manual button, you get here the 2D view of the spectrum. You can zoom in with the mouse, and you see here green stripes. And in between the green stripes, the system will scan the spectrum. So in this case, it's 4 pixels. You see it also here, it's called span. And the red line is the center line of the scanning. But the scanning is not even horizontal. If you go to the very left side, with this double arrow, you say, okay, the scan on the left side is also okay. If you go to the right side, you see it's also okay, so it's really fine. You can go to the center, back, and you see there is an angle of 0.055 degree in the scanning. So you can all these parameters you can change by the numbers or by the sliders, and you will get immediately a response in your graphic. But in this case I say it's okay, I use it, so I cancel this manual operations. And normally I would go through each spectrum and look if the scanning was precise or not. I know it from this example because I know it very well. It was precise in all of the spectrum, and you can use the automatic scanning. So what we can also see here in the spectrum is that we have different levels of ADUs of the continuums. So it looks a little bit chaotic. What we can do is to make an ordinate normalization only for the view, not in the data. If we click here and say, okay, we all want to normalize, for example, in this area, then you get a normalized view with 1 in the average of this area I have defined, and you see here the peak of this emission. So the next one is the sky background. The sky background is really an important thing. So you have to subtract the sky background from the spectrum to get a realistic data. So also here there's an automatic behind. You can also go here in the 2D view. Go back to 1, and you see here the yellow areas are the automatic found background areas. So I'm not so happy with this, so I want to have a little bit smaller scans and closer to the object. So you can do that manually. If you click, for example, above the spectrum, the upper bar goes down, and if you click below, the lower go up. And what I do is to check where is the limits to the spectrum, because we do not want to subtract an area where the spectrum is seen in the background. So what I'm doing is to switch off the lower bar, so we can see in the graphic only the upper bar. So I want to have, for example, only 10 pixel width, and you can go down and look where is, okay, that's too near. You see in the background now the spectrum, that's nothing. And you can go up, you can also enter here numbers and go up. It's too close for me, so I will go, for example, 85. Okay, you see here the background, and I have two possibilities to subtract it, pixel by pixel. Then it's possible that you get this noise into your spectrum. This is only necessary pixel by pixel if you have emission lines of light pollution. But if you have no emission lines of light pollution, like in this example, I take the fifth polynomial curve, which is a little bit seen here in the background of the curve. Okay, so I'm satisfied with the upper part, so I make the same with the lower part. So, for example, let's go away and go then to here. Okay, that's too close. Go a little bit down. Okay, that's fine. This is only a hot pixel or whatever. And now I enable post parts. If I enable post parts, you get an average of both areas. Okay, now you can do that for each single spectrum, or if you know that the spectrum stripe has not moved in the y-axis, you can use it for all. In this case, I know it, I use it for all, but you can go through each single spectrum and look if it's true or not. So, okay, what we can see now is this blue scale is for the summarized spectrum. So all spectra, single spectra, are summarized in the first spectrum. So we see the summarized spectrum has a peak of 4.062 relative to the continuum. And if we deselect sky background correction, you see the peak is only 3.906. So that's really relevant to have this sky background correction.
Manfred,
Yep.
what does it mean, high background?
Sky.
Sky background.
Sky background, yes. Okay. So, yes, please ask your question immediately, so not after my talk, please.
Yeah.
Yeah.
So sky background should depend on the exposure time. So for bright stars, it's probably very low. Or, yeah, just a few things together. Do you think it's only sky background or scattered light inside the spectrograph? Or both?
Both.
Both, yes.
Okay.
So, principally, you have it on the chip, so you have all light you get, you have there. Okay, what we can see is if we zoom into the graphic, this is not well aligned because of temperature shift over in this night. And I told you I've taken this data because we see here extremely the temperature shift. And if you look at the reference lamp, we see exactly the same. And that's the reason why you should do reference images always after each single spectra image. Now I think there is a big advantage of this software against other procedures. The alignment is here in the scanned data, in the 1D data, and not in the 2D data. Some people work with alignment in the 2D data, and I do not know if it's really so accurate as in the 1D data. And also, if you have it in the 2D data with Giotto or other programs, and you do the same procedure on the spectrum, on the reference lamp, I'm not sure if they are really in the same way aligned. But here, the software works with the 1D data, and I have an algorithm who goes to a hundredth of a pixel to align the single spectra. So, if we press align, we can choose want we align on the spectra, on the references, or manual on one of both. I try to do it in this example with the references. Wait a minute, a second. And what we can see, yes, they are fine aligned. We go to the spectrum, and what we can see, oh, it's not so fine. The reason is that I expect that one of the reference lines is not accurate for some reasons. So what I do is remove the alignment. So we have the status as before, and say, okay, to get sure, I want to align manually in the spectrum. Align the spectrum manual. The spectrum. Okay, that's right. So you can zoom into a line. You can also lock one axis for zoom. So for example, if you want to zoom only in x-axis, you lock the y-axis, and you zoom only in x-axis. You search for a line of your desired line, and you try to press about in the middle of this line. So in the middle of the y and of the x-axis in this line. So now we go through each spectrum and press about in the middle so that the system can identify what you want. And you see here it's well aligned. And what we can also see is, there is the orange is not aligned. So this one is the wrong. Now we can see, okay, where is the orange? It could be the third. We can disable the view of the third one. No, it's still there. Could also be the 7. I disable the 7. Yes, it's the 7. And I will remove this file from the project so that I have only the well-aligned reference lamps in the calculation. So, and that's the first step to bring the spectrum from the 2D data in the 1D data. Now we can save it, or we can say we save it and go to the next step, to the wavelength calibration. Yeah, the system said where the spectra are stored, so you get for every step a new directory with all the single spectra and the summary of the spectrum, and you can follow it later if you want. Also the references are saved, and now new windows are open for the wavelength calibration. What you are seeing now in the graphic is that you have an overlay of the reference lamp and the spectrum itself, and both is only shown the summarized of both. That's not meaning that the single spectra are disappeared. No, that are in the background in the calculations. But for the better overview, we have only the summarized of both spectra. Also, you can see this is an absolute ordinate in ADUs, and the strength of the reference lamps is much higher than of the object itself. But for a better view, we can also say, okay, we want to stretch the spectrum. Then you have also a very good view from the spectrum. And if you want to see the ordinate of the spectrum, you can click on it, and the ordinate change to the right one. So you can change this by clicking on the name. What we need for wavelength calibration is wavelengths, known wavelengths, and my system is working in this case that you have text files, simple text files, comma separated, where you have the wavelength defined, and you can have also a short name and a long name there. And I suggest to make for each setup your own file. So for my example, if I observe the H alpha with this 2400 lines per millimeter rate, then I have one setup for my argon neon lamp, which I can expect there. So not more. You can load this. So in this case, it's argon neon H alpha called for me. And if you load it, you get the list there. And if you have stored it, you can also have it under the same name, a JPEG. Then you get also an overview that is easier to find the lines in your spectrum then. So now we have to define the lines in the reference spectrum. The system can find it automatically. For example, if I give a sensitivity of 10 here and say find lines oh, there are a lot of lines, maybe too much for me. I can go deeper in the sensitivity. Okay, now I've not so much lines. The important lines are all there marked. But you can define it also manually. So, okay. What the system is needed is 2 points, 2 known lines of references, and the best way is to use the very left and the very right one. For example, the very left one here, 6483 argon line, is this one. You click on it, it's marked now, and you click on the corresponding wavelength, and you get here an entry in the list. We do the same for the last one, it's 6666 argon. This is this one. So we click on the line, we click on the enter, the wavelength, and we have 2 points defined. With an error of 0, it's clear. 2 points cannot have an RMS error. But you can now click on the other known lines and the system finds the corresponding wavelengths by itself. So I click on the line and you see a new entry, and so on. I do not use the H alpha line in this case because it's too broad, it's not accurate enough. I use only the argon and neon lines. Oh, now I have 12 values, and you have automatically calculated the RMS error. It's in the moment a line, it's linear, because the polynomial is set to 1. And you see here a lot of numbers. The reason is there are different possibilities to define the center of a line. One is, I call it X top. That's the top of the Gauss curve. One is called here the X bari, this is the barycenter of the Gauss. And the X center is the center of the defined wings entries, links are left and right. And for each of them, I calculate an extra value and an extra error. And the best values are on the right side. So, now we can go with the polynomial higher. You see the errors decrease. And with 12 points, I would go to 3, maximum 4 polynomial. And I would not be satisfied with this RMS value. So now we can look why. We look at the numbers and see, oh, there are a lot of big numbers. Let us look, for example, at this one. This is very big. And we zoom in. Okay. Could be a blended line, or there is another problem. We can try to define our area of Gauss fit by ourselves to make this a correct line and say, okay, I want to define it from here to here and see what's happened. Okay, it's not really better. What we can also do is to clear the selected line. Then it's out of this list, and it's still not really the right thing, I would say. So we try to find another one which could be the problem.
Manfred?
Yeah.
What about the sensitivity? Right now,
Yeah.
it's only on.
The sensitivity is, the sensitivity is only to can automatically identify lines.
Yeah.
That's only that you get these vertical lines here, these red lines, and then you can select your desired
It
lines.
means if you would increase the sensitivity,
You get more lines.
to a value of 50 or 100, what would happen?
You get a lot of lines. You have, if you have 100, I think you have 1,000 lines here.
Yeah.
But you cannot use it because these are only these small ripples or so also identified as lines. So the sensitivity is meaning how strong has to be the line outside of the continuum that it's automatically found. But for example, Ernst do always their calibration is defined by manually the lines, not automatically. So maybe they have immediately the better result, because what we can see here, for example, is this is not really found the right place for this line. So we will redefine it and get a better result. Okay, I think you know the principle behind this wavelength calibration, and we can, I think, another 10 minutes play around and get a really good result. I have done it often with this example. If you have done this and you say, okay, with this RMS value, this is a good value for me, you can save this data. If you save this data, you get the question, want you to save in the original resolution or want you to save it in a higher resolution. What is the reason behind? Resolution is in principle the pixel of the camera. And we made now a correction of the curves which are in subpixels. So you lose something if you make it in 1 by 1. For the most things, it's enough 1 by 1. But if you have a really precise radio velocity measurement, you can go to 2 to 1 or 4 to 1, then you have a bigger number of X positions and a bigger file, but it's more precise. So I will go to 1 to 1. And then you will ask, if you only interested on the summary of this spectrum, or do you want to have in the result all the single spectra? For example, if you want to compare what we heard today from here, of the pulsation influence on the lines, you want to have each single line. But in this case, I want to have the summary because I made this different spectra only to get a better signal to noise. So, and now we come to the latest part of this program, the post-production. Now, post-processing. And in principle, you can go from left side downwards, middle, and so on. So, the first thing is to correct the instrument's response. Very important, I think. You can do this to make an image of a reference star, make the instrument's response with the software, for example, and correct it with the result. If you do not have made this, you can use a reference star of a library. The best is you take the same star, if it's possible. For that reason, I have different libraries included. So the one is the MILES. This is a middle to high resolution library. Then I have a library with low resolution with all the types of stars we know. And then we have the LOD, and this is my favorite. But in the LOD I've only included the stars of my interest in the moment, and it's very easy to download from LOD side the spectra and include it in this. You have only to copy it in this directory. So I use now the LOD VV-SAFI, and what you can see now is that we have here three sections. One is the reference, the LOD reference in this case, and calculated continuum. It's not easier for such a star to make that. And what you can do is that, what we want to do is that we avoid the emission, because the emission is changing, so we can cut this. We can say, okay, we want to cut the emission from here to here, for example. Then it stretches automatically, so you get a better resolution in the view, and you can click on it, for example, on this points and shift it as you think it's the best to get the shape of the continuum. So now we can do the same for the spectrum itself. You can also say, okay, we want to cut the emission and correct a little bit these points. Okay, and the result shows now this red curve as instrument's response correction curve. What you can do also is to make a polynomial over it. So if you have a polynomial of 1, you have only a straight line, or you can go higher with these polynomials. So, and if you're satisfied with it, you can also store it as preset and use it next time on the same object, so that's not necessary to make all these steps. So we will apply this. Okay, now we have the correct instrument response. The next one is to scale the ordinate. We have still this ADUs on the left side. You can do this with mouse area, but I do not suggest this. You can do it with entering here the area of the wavelengths, or you can do it with presets. You can also enter here the values and save it as presets. I have it here, because you should always make the normalization of the ordinate in the same range to can compare the different spectra. Okay, now you see also here the numbers of the wavelengths area. You can crop the spectrum. I crop, in this case, always in the same wavelength area. Makes sense to can compare the spectra. You can also save it as preset. Next one, you can calculate the signal noise ratio. It's not easy on this object because it's an hamster. We can try to find maybe an area with no line, but it's not really representative, and do it with the mouse here. Normally you can also use a preset that you have always the same area for your signal noise calculation. The same we can do for the equivalent widths. Also makes sense to have a preset to have always the same range. Then you have the value of the equivalent width. Then it's necessary to complete the header data. So now we have the header data which was included in the FITS files. What we can do is get from Simbad. If you have here the name of the object, you can get it from the Simbad. If you have no internet, like me now, because I have not the VLAN activated, then you can also have a preset or enter it manually. Also for your observer location, you can save it as preset, so it's you can very fast enter this data, and also for your instruments. Okay, and this header data are necessary to calculate the heliocentric correction. So the heliocentric correction is here in principle the correction of the speed of the observer against the sky. So that means the rotation of the Earth, the Earth around the Sun, and also the influence of the Moon. And it's necessary to know the position of the observer on the Earth itself. So that's necessary that you have here the correct data entered. So we calculated, also date and time is necessary, and that's automatically found by the system because it's the center Julian date of the complete exposure series. You can apply it, then you get a change here in the x-axis, a little bit, a shift. If you do not apply it, you see that in the header that the velocity is this value, but it's not applied. Okay, what you can also do is remove the Lurix. It makes no sense in this object, but there is also a feature, I think it's unique, that is if you have the telluric references here, you can choose between two sources, but you can have your own source also. You can change the parameters like in each other program for the complete telluric spectrum, but you can also modify each single line. Because in my experience, the telluric lines are not always stable in the ratio together. So if you want to correct tellurics, it makes sense to also to have the possibility to make each single line correct in an extra way. Okay, and then you can make also documentation. If you press on Add Title, that generates an automatic title getting from the header. If you add a legend, you get an automatic legend of all relevant data you have done with the spectrum. So for example, here the range of the signal noise, of the equivalence width, heliocentric range and so on, and all other data of the header what could be necessary for you. But you can also edit this data after that. You can add a text. For example, if you click on it, you can change also the size and the color, and you can also set it on the right position you want. You can also add a line, a vertical line, so to mark something in the wavelength. Okay, and then you have finished. Save it. So I name it test for this example. And next time, if you come back and want to see your data, you can open it here. And you will see the spectrum and all the documentation. Why? The reason is because there are two files now. We go into this folder, and you see that's the FITS file, and you get an additional text file where the documentation and the positions of the documentation and all these things are included. And if you go back, we see there are new directories like instruments response. You have a FITS file for the instruments response. You can use it for other things. You get a directory for calibration, reference lamp calibrated. You see here the summarized and the single one. You get it uncalibrated for Spectra, also calibrated, uncalibrated. So you have the possibility to go into each area you want in the later times. Okay.
Yep. Could you go back to one of the early slides where you showed where you selected the spectrum in the 2D?
Yeah. So in this case, I will open from the stored data the uncalibrated reference. Reference uncalibrated, summarized. And for the spectrum, the uncalibrated spectrum summarized. Okay.
So it was where you were selecting the zones of interest, the strips, right at the beginning. You were selecting a vertical zone of interest to define the spectrum. You call it the scans or something.
Where you
The row spectrum.
Ah, you mean from the in the 2D state?
Yeah.
Ah, oh, sorry. Okay. So we open the raw spectrum. Here.
So where you're selecting the strip of interest,
Yeah.
you had a slider and you could.
Yeah.
Yeah. It seems, if you zoom in, it seems very narrow, and it looked like you were missing some of the signal. I don't know, is that deliberate?
You mean the span is to?
Yeah, like there's signal above and below the extent. I just wondered why you did it like that.
So what you see is between these green lines,
Yeah.
there is an average of all these pixels.
I think he want to get the dark, the spectrum of
The sky background.
of the sky, of the dark sky. How you can get it?
No. It looks no. It looks here. Yeah, just above your green line. Yeah. You turn up. It's more obvious like that. Outside your narrow strip, it seems like there's still significant signal.
Yes, this is, but you get yeah. In this, you see that's like a Gauss curve. It's go lower with the signal, and you know that the lattice has a tilt, and in the moment I have no tilt correction. So I prefer to make smaller stripes in scan. So it's a little bit loss of the data, but in my experience it's better to do that in this way.
When you make the correction for the temperature shift of the lines in the spectrum,
Yeah.
do you actually interpolate the comparison line spectra, the observing times of the comparison line spectra, 2 times of observation on midpoint exposure of your target star observation?
Yes. So the system looks at the timestamps of all images and of all references and correlates this data together. So, and also what's also important is the scan. So if the system search for the parameter of scan in the spectrum, and exactly the same parameter are projected on the reference lamps spectra. So because you notice, so not vertical lines as such as things, and you need exactly the same position on each pixel as in the scan of the spectrum. Yeah.
Manfred, what do you think about, in my opinion, about a nice improvement of this program? An improvement where you can create and scan a not in this way. What is this?
Horizon.
Huh? No, you know, horizontal. What
Yeah.
is it? Horizontal. Yeah. No. Totally in the other direction. From the top of the total spectral type to the below limited scan against the other direction.
Yeah.
Yeah, to get an information about the distribution of the pixel intensity within the total struct. And you remember we talked about this topic in Wuppertal.
Yeah.
And what you get is more or less a Gaussian distribution of the intensity.
Yeah.
And if you take the half-width maximum of this Gaussian distribution, could be the optimal area for the spectrum scan.
The system do that.
Sorry?
The system do that automatically.
The system do that.
But if you take the system parameter of scan, do that exactly what you say. It make 20 areas vertical scanned and make the half width exactly what you said. These green stripes are exactly on this
scan
position.
And this full width half maximum width of the Gaussian distribution is the parameter for the brightness of the scan.
Yeah.
Of the scan
Yes,
here.
I call it span. It's this highness of the. Yeah.
Andrew,
Yeah.
the most important question. Where can we get this sophisticated software?
Yes, okay. It's from myself. It's from a homepage, free to download. So if you enter www.astrophoto in English, so PH .at, then you find the way to the software. Very easy. Yes?
If the spectrum in the 2D image is not exactly parallel to the pixels, if it's at an angle or maybe even curved, does that work also?
If it's not parallel, it's not a problem in the moment. So because you see it's also not parallel, it's an angle of 0.055 degrees. It's right calculated here, but in the moment I cannot make a curve, for example. So I want to work in this way also, but I have no time at the moment to improve this. Yeah.
So you showed that so you had the half range after extraction, and then you subtracted the dark. Was it collapsed and then subtracted, or did you subtract the dark from your original science frame, pixel by pixel?
The dark is pixel by pixel, yes. Yeah.
About the telluric lines, I think, as far as I know, it's some data reduction pipelines. So the wavelengths of the telluric lines are fixed, and that's how they find corrections to the wavelength calibration. So they're not supposed to move.
Mm-hmm. Okay.
They may probably, I don't know if the atmosphere is too turbulent or it's just some rough ideas, but typically we know all these wavelengths, and if there are shifts, then those shifts are
from a bad wavelength
calculated,
calibration.
averaged, and then subtracted from the calibration, which is
okay.
assembled this.
So the result of what you say is that if you have a shift in some lines, then you expect a bad wavelength calibration of the spectrum. Yes.
Yeah, and that's what, for example, is done at the Canada-France-Hawaii telescope. It's a very high resolution, 65,000.
Yeah.
And when I compare positions of the lines in other spectra, I see that typically shifts are the same. If there is if I have a spectrum taken at some other observatory, which does not have that good calibration or does not take into account the telluric lines, I always find shifts.
Okay, thank you for this
They're
input.
supposed to,
Important.
basically, the bottom line is that they're supposed to be stable.
Yeah. But they are not always stable in the ratio together.
In the ratio,
This is my experience.
In the ratio, I think, I don't know, I still want to explore that. I thought that most of the lines, except maybe the faintest, because you just need to know where the continuum is. Typically, the ratios also pretty stable.
Mm-hmm.
Supposed to be, I don't know. They fluctuate with the humidity, with the amount of water vapor in the atmosphere, but the ratios of the lines, the strengths, should not vary much, at least.
Mm-hmm.
Again, that's maybe a subject for a project.
Yeah, thank you.
Wavelength calibration of telluric lines is, from my understanding, only to find the right way how I fix the position of one of the tellurics with Gaussian fix or with several.
They're supposed to be Gaussian, yeah.
This optimal.
But it depends on the instrument response.
Yes, of course. Yeah.
So it's instrument dependent.
Yeah, because the wavelength of the different tellurics are stable all the time, wherever you are. Yeah.
Just one of these.
Okay, no more questions? Thank you.